So I'd like to start by thanking the organizers for inviting me to this lovely conference. Is this big enough to see at the back?
Yes.
Okay, thank you. Okay, so maybe okay, so I'll start with the most important thing, which is this is joint work with Nicolas Bergeron and Pierre Charollois. And there is an archive preprint 2311 0411. Okay. Right. Okay, so yes, I want to talk about a conjectural construction of units living in certain number fields. And so the main point of this talk is presenting a conjecture and some evidence for it. And the setting is that of explicit class field theory. So maybe start by talking a little bit about that. So what is explicit class field theory? I'll start with a number field K, and one looks at extensions of K that are abelian, meaning they are Galois with abelian Galois group. And one would like to construct such extensions. And so maybe let me phrase it like this. This field is contained in what I would call KAB, which is maximal abelian extension of K. Of course, it's an infinite degree field. And so class field theory describes the Galois group of this infinite degree extension in terms of data that are intrinsic to K. And so explicit class field theory is about constructing KAB, which is a completely different problem. And so let me talk a little bit about some very classical results just to put our conjecture into context. So, so the first classical case is when K is the field of rational numbers Q. And in that case, if I give myself an abelian extension of Q, then the famous Kronecker-Weber theorem says that there exists some integer such that L is contained in the cyclotomic field obtained by adjoining to Q and nth root of unity. So this is, of course, very classical, and in terms of this problem of explicit class field theory, I can rephrase this simply as saying that UAB is just a union of all these cyclotomic fields. Okay, so this is somehow the ideal theorem. We have these explicit elements, namely the roots of unity, and they generate the maximal abelian extension. Then we have the other case that's very classical is where K is imaginary quadratic. So I will let K be U adjoin square root of minus D, where D is a positive square-free integer. Right, and so So here there are many results. One of the things one can look at is a particular abelian extension called the Hilbert class field. And there the Hilbert class field for these imaginary quadratic fields can be constructed explicitly. Namely, one takes E to be an elliptic curve with Cm by the ring of integers. Okay. And then one looks at its J invariant, which in principle is a complex number, but so I mean an elliptic curve over the complex numbers, if you will, with complex multiplication by OK. And so the J invariant is a complex number, but in fact, the fact that the elliptic curve is complex multiplication guarantees that that number is algebraic. And the theorem there is that the Hilbert class field is obtained by adjoining to K the J invariant. Okay. Right. And in fact, for today's talk, what's interesting is how to construct other abelian extensions where one allows for some ramification. So let me talk briefly about that. So I choose an ideal inside OK, and then I can look at Km, which is the array class field K of conductor M. And so this is an abelian extension of K, and it's characterized by the property that it's the maximal abelian extension that only ramifies at M. Okay, so there is also an explicit way to construct these fields. And for that, one can use elliptic units. And so how does that work? So again, I'm going to construct these fields by adjoining, or maybe I should say, I will go more interested in constructing particular elements in these fields rather than construct the whole field in what I'm going to say. So I'm again going to construct interesting elements here by evaluating some interesting function. So let me take a lattice L of the form Z alpha Z, which has Cm. Okay. And I'm going to consider the following theta function. So I know theta 0, which depends on a complex number Z and on the lattice L, and which is explicitly defined by this infinite product. So n varies over the non-negative integers, and I take the following. Sounds right. 1 minus q to the n plus 1 times qz increase. And here the notation is the standard notation. So q is what could be called q of tau is e to the 2 pi I tau, and qz is e to the 2 pi I z. So this is given by this very nice infinite product, which converges very nicely because I'm taking tau, of course, to lie in the upper half plane, and so this makes the modulus of q strictly less than 1. So this is a convergent product, and so this converges to a holomorphic function of z, n of tau, and the zeros. So of course, so since the product converges, at least we can read off what the zeros are. It has exactly simple zeros when z belongs to that. Okay, so that's the function I'm interested in. And right, and so this function has some interesting properties that I want to point out because I'm going to soon talk about a higher analog of this function. And so these properties are very easy. So if I add 1 to z, the function stays the same. But if I add tau to z, then the function gets multiplied by a simple factor, which is minus qz inverse. Right, okay, so now what is the relation with the explicit class field theory? I'm going to choose some additional data of the form of another ideal that I denote by A inside OK. Not the unit ideal. And I'm going to define functions that I denote theta L. And this is a quotient of values of the theta function. So I will take 12 times the norm of A here. Oh, and I can raise to the top. Okay, so right, so it's a quotient of two theta functions, except I'm changing the lattice. I'm taking L, but I'm also multiplying by the inverse of the ideal A, so I get a bigger lattice. And so I obtain this function here. I'm also raising the numerator to this power 10. And so one advantage of this function is that, well, it's very easy using these properties to check that this function is in fact elliptic for z.
Sorry. Is n norm or is nm norm?
No, nm is norm.
So it's not the norm, it's m times a. We also
No, sorry, this is not a Gothic m. Sorry, yeah. So maybe I should say norm.
It's just n.
I should be not n of a, the norm of a. So this is an elliptic function of z. And so I can think of it as an element of the field of non-zero element of the field of random functions on E, where E is C mod. And now the idea is that this function is, well, both the elliptic curve E and this function are defined over the Hilbert class field of K. And so I can evaluate it at the torsion point for this elliptic curve, and I will obtain an algebraic number. Take so maybe I should say evaluate at some point P, which is in E, but not in the A torsion of E, which is where the divisor of this function is supported. And so I know I obtain a non-zero complex number. And in fact, this non-zero complex number will lie in this field. So this is a field. So this gives a construction using this function of elements of these Ray class fields.
P is inequality.
Yeah, sorry, I didn't say what M is. Sorry. P, but I want P to be M torsion. Sorry. Right. Okay, so that's the idea. And okay, I won't go into more details, but I also should say that this is there is some explicit Galois segregation. Is explicit. So in other words, if I take an element of the Galois group of Km over K and I apply it to this element, I can describe the element I get. Again, it's an element of this form for some other P. There's this thing called reciprocity law. And so this is very useful because in practice I can really use this to compute the minimal polynomial of this unit over K and check, and really have a construction that numerically works very well. Okay, so before I go on to what I wanted to say, let me just say something briefly about what is known about this problem of explicit class field theory for other fields. So for imaginary quadratic, I just told you a bit about it. And so maybe I'll just say that I don't have time to survey all of this, but there is quite a bit of recent work using p-adic methods to generate these fields. Yeah, there are many names I should write here. I mean, certainly Dasgupta and Hecke and Darmon and Wong and Pozzi and others. Yeah. So, yeah. There we go. And there is also some work on Archimedean methods, although here the results are much less definitive. So basically here we do have some, there's some recent breakthroughs, for example, the work of Dasgupta and Hecke, which combined with previous work of Darmon and others allows a very similar construction of units in abelian extensions of real quadratic fields. And for Archimedean methods, there is the work of Riemann-Sech, which is the closest one to this talk, and of Charollois and Darmon. So maybe if I have time, I'll say something about Riemann-Sech at the end. Let's see if I can do this professionally.
We'll give you a grade at the end.
So.
Is it before?
We'll see.
Okay. That's not bad, right? Okay. Okay. So this talk is about complex cubic fields.
Excuse me, in the real quadratic case, there is also Stark units.
But these are conjectural, of course.
Well, yeah,
But so are the Archimedean methods there or no?
Yeah, so yeah, maybe I should clarify that. So the Archimedean methods are all conjectural. The p-adic methods are sometimes not conjectural. There is now proof theorems that say that a certain p-adic rigid function produces Stark units. Yeah. For real quadratic, and I think in some cases for totally real fields, but I'm not really an expert. So, yeah. Okay, so I want to talk about complex cubic fields, which in particular are not of the p-adic method. Right. Okay, so I'm going to fix my complex cubic field, and so it has one real embedding that I will denote by sigma r, and I will also fix one of the two complex embeddings and call it sigma. Right. Okay, and I want to talk about a conjectural construction of units in Ray class fields. So here F is an ideal book. And the idea is that these are constructed in a way that's very similar to, or sort of very reminiscent of what I just said about elliptic units. But instead of using the theta function, we're going to use the elliptic gamma function. So I'm going to talk a bit about this function, which is a much more function that was defined much more recently. So let me first tell you what it is. So I fixed three complex numbers, z, tau, and sigma. And I'm going to take tau and sigma to have positive imaginary part. And then I can define this function, elliptic gamma, of these three arguments as follows. So it looks like this. 1 minus q tau, let me get the sign right. K plus 1, q sigma, k plus 1, and q z minus 1. And here I have q tau to j, sigma to k.
Should we think of the three variables as the Siegel matrix in the Siegel half plane?
Yeah, no, so it's related to SL3, in fact, not to SP4. So I'll talk a little bit about the underlying arithmetic group for this construction in a moment. So maybe one should think of this function as more or less, it wants to have 3 periods which are 1 tau and sigma. But of course, it's right, if one fixes tau and sigma and one looks at the function of z, yeah, it wants to have these 3 periods, but of course you can't have 3 independent periods. So, well, it somehow manages this by only allowing j and k to vary in certain quadrants, right? So j and k vary independently from 0 to infinity, but I only but they both have to be in this first quadrant. And so, yeah, so maybe I'll say that this has 3 periods, 1 tau and sigma. And so, okay, what do I even mean by that? Okay, I mean, that means nothing, but what I mean is that at least we have these transformation properties. If I add 1 to z, the function stays the same, which is obvious from this. I mean, everything I'm going to say here is very easy, follows very easily from the product. But when I add tau to z, what happens is I get the previous theta function I was talking about, evaluated at z and sigma, multiplied. I get my value, and similarly for adding sigma to z. So it has this property which hints at some sort of hierarchy before we had the theta function, and so the factor we had in front was a simple exponential. Now we have this elliptic gamma, and the factor we have in front when we translate z is the theta function, which is like the previous number in this hierarchy. And so in fact the hierarchy continues, and there is a function of 4 variables which will have similar transformation properties, but will have the previous elliptic gamma function appearing and so on. Okay, so right, and maybe so these are very easy. What's more surprising, is a property that one can call SS3Z modularity. So maybe I should say that so the function was studied in a lot of detail by Felder and Marchenko in some papers appearing in the year 2000, I think, around 2000. They say that the first time that was really given a name was by Reisner in 1997. But what I'm going to talk about here is due to Felder and Marchenko around 2000. And it's the property that somehow generalizes the modularity property of the theta function above that I'm going to talk about. And it looks like this. Well, okay, it's a number of properties, but let me write down suggested one. So, right. Yeah. So it looks like this. I act on my, I could make this change of variables in my vectors z over tau minus 1 over tau, sigma over tau. And what I get is just some simple factor of z sigma, so some simple exponential factor where p is a polynomial in z of degree 3 with coefficients being rational functions in tau and sigma. And then I get this gamma value I started with, but I also get a third factor, which looks like I have sort of changed tau and sigma. So z z minus tau over sigma minus tau over sigma minus 1 over sigma. So that's the transformation property, which is related to, so in fact one can encode this into an action of SL3Z in these functions. And so, yeah, so the idea is to imitate the construction of elliptic units replacing theta 0 by elliptic gap. So I want to
You want tau and sigma to be globally different.
yes. Okay. So the next thing I'm going to do is present an example. So hopefully that will clarify what I mean.
No, but I mean, they still imaginary parts are greater than 0 for tau.
Well, okay, yeah. So maybe I should have said that. So one extends this. So one can extend this to tau and sigma being both not real. Okay. So in fact, for this transformation law, sigma over tau could also lie in the lower half plane. So one wants to extend the function there.
But even if they're both not real, the quotient must be real.
So I mean that tau and sigma have to be either in the upper half plane or in the lower half plane, but not on the real line inside the complex numbers.
No, I know, that's what it means not to be real, but
Okay, sorry.
that they're in the upper lower half plane, but their quotient could be real. Or you mean they're both in the upper, both in the lower, I think.
No. They go. Okay, so yeah, I mean, so we should take this to mean whenever all three factors have their second and third variable not real. Okay, that's what I mean. Okay, so
It was
Which
just
is still strange. Why did I see you have 0 per sigma on the right also?
okay.
There are two factors that they want.
Okay, so let me give an example just to clarify what I'm talking about. So the example is I start with this complex cubic field. Q adjoin the cubic root of 7, or rather, well, let me put it like this. It will be Q adjoin beta, which I take to be inside the complex numbers, where beta is the following non-real cubic root of 7. So beta cube is 7. Okay, and so I'm going to fix the ideal in OK, unique ideal whose norm is 3. And then I can consider its Ray class field, which is a totally complex number field of degree 6 over K. So it's cyclic, so Kf. So the Galois group is cyclic of order 6. And so I will take a generator of this class group that I will call sigma. And now I'm going to look at the following. So I will take, for tau, I will take 2 beta plus beta squared over 15. And for sigma, I will take minus 2 plus beta over 15.
Sigma is not equal to sigma.
Yeah, oh yes, thank you. Yeah, sorry, so maybe I should call it something else. I don't know, alpha. Yeah.
So alpha is the...
Yeah, alpha is the generator of the Galois group, sorry. Okay. Yeah, so the Galois group is cyclic of order 6, and I'm choosing a generator calling it alpha.
Okay, but you actually had a third meaning of sigma. Sigma was the non...
Yeah, sorry, no, that's why I changed. No, so tau and sigma are complex numbers.
That was the second, that was the third. Sigma before was the non-real embedding.
Oh, yes.
Which is now the identity.
Oh, yes.
You have
Yes, this is yes, thank you. Okay, so yeah, sorry about this. Okay, yeah, okay. Okay, so yeah, I'm just going to not change that now. So I'm going to confuse myself. If it's unclear, please ask me after.
We can have sigma of sigma.
Sigma of sigma.
Yeah. Yeah. Okay. So these are complex numbers. Okay. And so I'm going to look at the following quantity. I evaluate gamma at 1/3 tau sigma raised to the power 5, and then I divide by the same expression where all the arguments have been multiplied by 5. And so this is a number that one can evaluate with quite large precision, minus 4.02, minus I times 41.85. Okay, well, so this converges quite fast, so one can easily get hundreds or thousands of digits. So the conjecture is that this is a unit in KF star. Right, in fact, this number is very close to a root of the following polynomial. Yeah, P is x to the 6. We have 6 beta squared minus 14 beta plus 2 x to the 5. 4 beta squared minus 6 beta plus 2 x to the 4 and minus 6 beta squared minus 152 beta minus 1 of 2. It's cubed, and now you'll be relieved to know that this is a palindromic polynomial, so I don't have to tell you what the other terms are. And so, right, so this is a numerical fact. You can check it using Paris. It's true to at least 1,000 digits. And so, well, because this polynomial is palindromic, we have, if a number is a root, then a complex number is a root, then the inverse will also be a root. And so we have just described conjecturally 2 roots of this polynomial.
So the fact that it is algebraic or something, it's a conjecture?
Yes, of course, conjectural, yes. I mean, I have.
It's a statement, it's the theorem that it's approximately equal to.
I mean, yeah, I can make this a theorem by telling you that it's really probably within 10 to the minus 1,000 of a root of this. But, yeah. Okay, so, yeah, sorry, where was I? Yeah, so, okay, so first of all, once you find this polynomial, you can ask Paris, what is the splitting field? And so the splitting field of P is now really probably KF, the ray class field I was talking about. Maybe the more interesting thing is that, so what are the Galois conjugates of U? Well, it's U and U inverse. And then we have, this alpha of U plus minus 1 and alpha squared of U plus minus 1. Right? But alpha was this generator of the Galois group. And so, yeah, so I have to say that alpha of U is also exactly the same form. So maybe alpha to the j, tau j, sigma j. 5/3 tau, 5 tau j, 5 sigma j. So here j is 1 or 2.
To the 5th power.
Yes, thank you. Yeah, thank you. So this is again numerical. Everything is numerical, of course. And now here, tau j and sigma j, well, I can't, okay, so maybe I'll tell you what tau 1 is. So tau 1 is 15 plus 2 beta plus beta squared over 150, and so on. There are explicit rational elements of k that we're evaluating this function. So it looks like this function, this particular function, with this fifth power here and divided like that, is really parameterizing all the Galois conjugates of this polynomial.
Do you have a theoretical understanding? Of what
No,
these
not at all.
properties are?
Not at all.
And without proving it, but just, so like Charollois reciprocity tells you how the Galois group acts, and even if you can't prove it, you can
So I'm going,
write down what it says.
I'm going to tell you about that, yeah. So
It says how you don't know it. You don't know where these tau j's and sigma j's.
no, okay, well, okay, maybe that was too strong. So I'm going to write a reciprocity law that looks very much like Shimura reciprocity law, okay, for this function, but of course conjectural.
Are you going to tell us where did you pick those numbers from?
Yes, that's part of the conjecture.
But the construction of P was purely numerical, right? I mean, you guessed it numerically, but once you guess it, you have...
Exactly. So the point is, I'm going to write a conjecture that certain finite product of values of the elliptic gamma function, evaluated elements of your base field, lie in a certain extension, and I'm also going to describe conjecturally the Galois conjugates of the element that you generate in this Ray class field. And so you just compute the symmetric function in these quantities, and now you know that they lie in the cubic field K, and then you can try to identify them.
Sorry, do you have a formula also for the real embedding or only for the function?
That's a great question. So the conjecture, which I would state, is that for the places of the Ray class field above the real embedding, the evaluation of these complex numbers is 1. So these are supposed to be, I mean, I will write a conjecture, and then a consequence will be that these are stark units. So you should expect that they are like. Okay, so so that's the example. So yeah, the thing I want to stress is that, so yeah, it looks like there is this Galois action on the values of this function, even though there is no, I mean, I certainly cannot see any algebraic variety anywhere in the construction. So yeah. Okay, so yeah, maybe I'll say.
So, sorry, what context does this function appear, and what did they define it for?
Well, so that's certainly not my area. I mean, I think it's mathematical physics.
Solving integrable models.
Yeah, it appears in mathematical physics somewhere.
There must be a reason why. Yeah.
Baxter equation.
Yeah.
Vadim gave a talk about this 6 years ago, no?
I mean, I will give, okay, the talk won't be entirely conjectural. I will give a theorem, which some sort of limit formula for these values.
I did not know about.
Right, okay, so I want to talk briefly about this, how to think of this transformation property. And so for that I need to, so this is also the work of several authors, Hilbert and Nicolas, and Zhu, and also probably further on Rochenko as well, they already wrote that. So they give some geometric interpretation for these transformation properties of the elliptic gamma function. So I'm going to look at a slightly more general setup. So I'm going to look at a lattice L, which will just be a free abelian group of rank 3, which I will also consider as oriented. Right. And so the idea is that before I wrote down this double product, which is the product over some quadrant, and so I want to consider quadrants defined by more general pair of two lines, rather than just the x and the y axis. And so that's very easy to do. I pick A and B to be functionals on this lattice, integral valued, and I will take them to be linearly independent. And so I immediately obtain, so not very good at drawing, but basically I have, so this is supposedly a picture of that. This is a solid line. So this is a picture of L tensor R, which is just R3, and inside there I have two hyperplanes, which are the kernel of A and the kernel of B. And so these two hyperplanes divide this three-dimensional space into 4 regions, and I'm going to pick 2 of those that I will call C plus minus of AB and C minus plus of AB. I'm going to, the definition is what do you think it is? And so I can now define a variant of the elliptic gamma function indexed by this pair A and B. And so it looks like this. I take delta to be in C plus minus AB. So notice that, so C plus minus AB is some sort of wedge that looks like this, but it contains this vertical line. And so I'm going to quotient it by, so this vector here, sorry, I should have said, this vector here, I will call, yeah, it's a generator of the intersection of the kernel of A. So gamma generates the intersection of the kernel of A and the kernel of B. And so, yeah, to look at this expression here. 2 pi I minus 2 pi I, and then I have z of delta minus w over z of gamma. Sorry, I need to tell you what the function depends on. And then I have this other product. Quotient by z gamma. 1 minus e to the 2 pi I. Okay, so yeah, so what does this mean? So this is a function that depends again sort of on 3 variables. The first, this variable is the lattice, Z3, and then I have 2 more variables, W and Z. W is a complex number, and Z is a homomorphism from my lattice into the complex numbers. Okay, so basically what I do is like I look at elements in my lattice that lie in one of these 2 quadrants, and I take this infinite product, which is really over this quadrant quotiented by z gamma. So it looks like again a quadrant in a plane in 2-dimensional space, and I take this quantity here. So if I take A and B to be something like the basis vectors in the standard lattice Z3, I recover the previous elliptic gamma function. Okay, so it's a slightly more general setup. But what I want to say is that, yeah, and so Z I have to take, it's basically defined on an open in this 3-dimensional space where it's guaranteed that these products will converge. Okay. And now, right, okay, so the properties I wanted to point out are, so let's fix A, B, and C. Now 3 functionals to be taken to be linearly independent, and I think in fact primitive. So yeah, it's primitive in this lattice. Then it's easier to understand what the transformation property is. Namely, if I multiply these 3 values, gamma AB times gamma BC times gamma CA, I get a factor like what I was writing before. So there's a certain polynomial depending on A, B, and C, which is of degree 3 in Z, and yeah, we have this property here. And we also have an equivariance property. That's obvious. If I take G to be in the special linear group of my lattice L, which is really just the group SL3Z, done, then if I act, I can act by G on all these quantities, and one sees very easily that we have this equivariance property. Right, and so, yeah, so it follows from these properties that, yeah, so if I fix A, I can consider the following map, sending an element G in the special linear group of the lattice to the function where I take gamma of A and then GA here. And then, so what is this? I'm also fixing my lattice L, and I'm thinking of this as a function of W and Z. This is, I'm going to think of it as a function, as a meromorphic function of W and Z, but modulo holomorphic functions on C times on C. So thinking of it modulo holomorphic functions means that I can just discard this thing, and this becomes just 1. And so I have something that looks like a cocycle relation. So this function is a 1 cocycle. For S of Bz. It's a cocycle valued in this space of meromorphic functions of W and Z. And so now I can at least explain a little bit, I can explain the main idea of the definition.
What are the variables in O of C the segments? That's W and Z.
Yeah, W and Z. So Z is a functional on my lattice, but complex valued functional, linear functional. And W is just a complex number.
But the units of order is basically just exponentials.
What's that again, sorry?
So you're working not invertible.
Yeah, okay, it's just a comment. I'm not really going to work with this, but I mentioned, I was just about to say, yeah, so, yeah, if you work modulo,
But you need more than just.
yeah, you need more than that. So, okay, so I think,
And I said, do you need more than just exponential polynomials?
well, so I was about, okay, so maybe I'll say one thing, which is that, so I think what I said there is true, but maybe I want to point out that one would like to promote this to an actual cocycle, not modulo holomorphic functions, but actually an actual cocycle valued in meromorphic functions, so one can evaluate them. And for that, it is important that it looks like A times some polynomial, because there is an operation called smoothing, where one does something like this thing that we did before, where we were considering a lattice L, but also the lattice multiplied by A inverse. And if you do this sort of process enough, that will kill this polynomial. And so, yeah, there is yeah, but I can explain this later. Right, so let me at least try to arrive at the general definition. Okay, so, right, so I just told you a bit about this setup for the elliptic gamma function. Now I want to come back to this situation of complex cubic fields in general, not just the particular example I was looking at. It's a bit dark in here. Should we turn on? I mean, I don't know. Can people see this well, especially
If you can put that on.
this? Does this help? Maybe?
No.
Okay. Right. Okay. So.
Okay, good question. Does this construction with cube root 7, does it vary or is it rigid?
No, it's rigid. You mean that the sort of relation that, this polynomial relation that I wrote down holds as you vary tau and sigma continuously, right? And not,
Or arithmetically?
no, well, I'm going to talk about other complex cubic fields, so in that sense it is more general than what yeah. Okay, so, yeah, so K is my complex cubic field, and well, yes, sigma is going to denote my preferred embedding into C, sorry about that. And I'm also going to now fix some additional data. So I will take ideals P and F inside OK. And so, right, and I will take them to be co-prime. And the yeah, okay. And I don't know if I will talk about this, but I'll just say it here. I denote by Q the positive generator for F intersect Z. Right, and so I'm going to look at this extension where this is the narrow Ray-class field. And I'm going to assume that Kf is totally complex. Yeah, otherwise the construction doesn't produce any interesting numbers. Okay, so and now, okay, so before I was talking about this rank 3 lattice. So the rank 3 lattice I'm going to be interested in is F B inverse. And so this rank 3 lattice has an action of a unit group that I denote by OF star plus. So these are the units in OK star that are congruent to 1 mod F, so U minus 1 is in F. But also, under my real embedding, they are positive. And so, in fact, this is just generated by 1 unit that I will denote by epsilon. So I can specify epsilon by saying that I want epsilon to have real embedding between 0 and 1. Okay, so right. Okay. Okay, so that's the lattice, and I need one piece of auxiliary data, which is another ideal A. Which I take to be co-prime with 6 times the norm of F. Right. I need that, and I also need. So the idea, okay, maybe it helps to remember how the construction of elliptic unit goes. We had this theta function, and then one considers a certain quotient where one uses an auxiliary ideal A, and then one also has to evaluate the function at some torsion point, which is my H here. So these play the same roles here. H will be a torsion point, and I won't explain exactly how to choose it, but there are some congruence conditions that one needs to impose for the conjecture to work. So modulo the ideas A, B, and F, one needs some congruence conditions. And so now I can do the following thing. So these are all fixed. So fix all these data. Then I can find there exists a unique ideal, functional, such that A of H and A of epsilon inverse H are both 0. And such that, so this is where one needs to be careful with orientations. So I said that my lattice is oriented. I didn't explain exactly how, but because I have chosen a preferred embedding of my cubic field into C, I can induce an orientation on this lattice. And so I also want that this is preserved orientation. Okay, so given all this data, there is a unique choice of this functional A that appears in this co-cycle that I was talking about, satisfying these conditions. And now I can define my number. That I will denote gamma AH of FP inverse. And so, okay. Okay, maybe I'll say maybe I'll take one more step. Gamma. So gamma A of W would be L, will be this quotient, W would be L raised to the norm of A. This is this raised to the norm of A, and then I divide by the same function, A epsilon A. Now with this, okay, so very much like in the previous construction, we have our lattice L, and we multiply it by A inverse, and we take this sort of quotient, which is now a function depending on these two variables, W and Z. Now what I want to do is I want to evaluate this function at some values, and how do I choose these values? Well, F inverse is the following quantity. It's this function gamma AH. So it's gamma A of sigma of H, sigma. Okay, so this is my main definition. So maybe let me clarify how this works. I have taken this quotient, which is a meromorphic function of W and Z, and the point is that these are infinite products. So at least I control exactly when they are 0 or non-zero. So I can make sure by choosing these values appropriately that I obtain a non-zero number. And so what I do is I have fixed my embedding of my lattice FB inverse or my cubic field into C, which is sigma. And so that's what I take for this value of Z. Remember, Z is a homomorphism of L into C, and I have a canonical one that I can choose, which is the one coming from the complex embedding of my cubic field into C. And for W, well, I have chosen this point, H. And so I can apply sigma to H, and I obtain a complex number. Okay, and now I can finish at this stage in the conjecture. So the conjecture in general is that these numbers are units in this field. That the Galois action can be described explicitly in terms of Shimura's, like very similar to Shimura's reciprocity law. So there is a canonical isomorphism of the Galois group with the class group with the narrow array class group of K of conductor F. And this isomorphism sends an ideal C to its Harting symbol, sigma of C. And so the conjecture is that if I let sigma of C act on this number, I obtain gamma AH of FB inverse C inverse. So I just act by multiplying the lattice by the ideal C. It's it looks very much exactly like how it looks like for elliptic units. So I hope that answers the previous question on how Galois acts on this. So there is also one. I'll finish in 1 minute if I can take 1 extra minute. So there was a question about. Basically this describes So maybe I should clarify that here. I mean, where Kf are regarded as embedded in C by an embedding extending sigma. Right, so KF is an abstract field, and I want to say that this is a complex number which lies in there. I have to clarify that this extends my complex embedding. You can ask what happens for sigmas that extend the real embedding. The answer is numerically again that the numbers we obtain have absolute value 1. And then finally, a theorem.
So what's wrong with absolute value 1?
Oh, nothing. No,
But there could still be algebraic, or is
yeah, they could still be algebraic. Yeah,
Are they on the computer? Or you can't.
Oh, it's just the same. It's just the same. Oh, and it's the same complex. It's the same algebraic number, but embedded with a different embedding, namely one extending the real embedding of k into c.
Okay.
That's all.
No,
Yeah,
but my question is, do you have a similar formless ratio of elliptic gamma functions for that embedding?
no, that's a great question.
So you have to
No, we don't have an explicit formula.
You have
for,
to actually recognize the number and then you have to...
Exactly. So, but so it's true. If we had that, then we could trace it down all the way to q, and we could find the polynomial, minimal polynomial over q. Now we have to do it over k. So this is true. You're right. Maybe the theorem I will write is the following thing. One can consider the partial zeta function corresponding to the ideal f and b, and consider this particular inner combination. Or maybe I should trace it like this. I take this quantity and I put ABS. ABS. And I look at this expression, I differentiate at s equals 0. This is equal to the logarithm of the absolute value of our numbers. So this is a theorem. So this is the analytic continuation of this partial zeta function, which vanishes at s equals 0. And then one can take its derivative. And it turns out that the derivative at 0 is logarithm of this number, which is somehow some not purely numerical evidence for the conjecture.
Dependence on age?
Yes, thank you. Yeah, I didn't say that. So part of the conjecture is that these numbers do not depend on age. And so this proves it. This proves that these numbers their absolute value does not depend on age. But we cannot control how the phase varies with age. So we made it part of the conjecture.
And so these are the candidates for Stark's unit.
That's right, yeah. So if you compare the conjecture with Stark units, what you recover is that this is some sort of Galois twisted. So it's a Stark unit to which you have applied a Galois twist. And so one can think of it as a formula for Stark units. Okay, sorry, I think I went a bit over time. Thank you.